a review or an overview. I mean, it'll be a combination. I'll look through the class and figure out if there's anything critical we didn't do that I can do in 15 or 20 minutes. I already know of one thing, but so I already know of one thing. I'll see if I can find other little stuff. Maybe try to tie some things together, and then and otherwise just have an overview. Wow, wow, this is for focusing. Yeah, almost. There you go. Okay. All right. So let me review quickly some of the stuff that I guess Leo talked about on Friday, which is integral action. And the basic idea is to observe here if you have this feedback loop, and if either P or C has a pole at s equals 0, that basically says that the loop gain is infinitely large. Well, according to our theory, that means that all the benefits of feedback come, well, in infinite quantities. It says basically that all sorts of things. It says that the sensitivity, well, it says, first of all, the transfer function from R to Y is 1. You can check that very carefully. Well, that's PC over 1 plus PC, and if PC is infinity, then infinity over 1 plus infinity is 1. Not only that, it doesn't really have anything to do with the details of P or C. I mean, as long as one of them stays infinity. So it says that if this, I mean, it's a crazy idea, but if it were to actually work or be possible, it would basically give you total insensitivity to variation, as opposed to merely greatly reduced variation. Okay, so that's the idea. And it turns out it does work, and it's widely used. It's widely used in this context, where your controller or feedback term has the following form. It's a proportional signal, that's Kp, right, plus and then Ki over S. So in the time domain, it says this. It says that the input U, which you feed to your plant, that's the system you want to mess with to drive Y to match R. What you send to this plant has two terms. One is proportional to the error, and the other is proportional to the integral of the error. Very, very interesting idea. So this term here is quite interesting. If you think carefully about what this term is, it's this. It says if there's an error here, which is the difference between what the output is and what you want it to be, that's R, that's an error. It says if you have a proportional control, it says that what you do is you turn I think of U as a big knob or a valve or something like that. What you do is you turn your knob or valve an amount proportional to the error, and of course in the direction that will correct the error. So that's proportional control. Okay? This term here is really interesting. It says that when there's a constant error here, what you need to do with U is first of all turn it in the direction that will drive the error to 0. But it says basically you do it linearly. You basically integrate how much E there is, and the longer there's an error, the more you crank this up. This explains why, for example, you get absolutely 0 tracking error. In other words, if there's an error here, as long as there's any error here, U will in fact not only be moving in the right direction, but it'll be increasing because it's an integral of this. Okay? So that's basically the idea. And so just to give a simple example, I guess Leo looked at our heating example last time, but I'll just talk through a very simple example. A very simple example would be, for example, an altitude hold system for an aircraft. So you have a radar altimeter, and radar altimeter is giving you the actual altitude. You dial in the altitude you want here, and there's an error. Now, your plant is the aircraft, and you can actually manipulate, you can actually move up or down by a combination of changing the elevators and changing the thrust in the aircraft. That's how it's done. So it's a combination of these two. You can think of it simply, though, as a single signal. In fact, it could be either one acting separately. So this could either be thrust or it could be elevator angle. Will change your altitude. Okay. Now, if everything were perfect, the airplane would just fly along at the right height always. But this is ridiculous because, for example, there's going to be small variations in air density, for example, that are going to cause the thing either to fall or to rise slightly. All sorts of things will change this. Even if you got the angle set right, your altitude would drift down anyway. It might drift down or up if your elevators are a little bit too far down. So there's no way it's going to actually just sit there exactly when you dial in 31,000 feet or something like that. So you'll get an error. And the question is what to do about the error. Well, you have a feedback control system. If you have proportional control, what it does is it looks at the error in feet, multiplies that by a certain angle, and translates that to a deflection angle on the elevators. Okay, so the units of C would be in degrees per foot. Presumably be a very, very small number because you'd hardly deflect these things for, anyway. So this is the idea. If you're low for some reason, E would be negative. And what this says is you want to push the elevators down so the thing will move up to a higher altitude, this kind of thing. Okay, so that's what that does. But it never actually completely corrects it. And the reason is, I guess you've seen it already, and also you've seen the arithmetic. It's just basically 1 over 1 plus PC is the reduction in the error. And 1 over 1 plus PC is not 0 in this case. Right? So it never quite corrects it. In other words, it moves you towards the correct altitude, that's for sure. But it doesn't move you all the way to the correct altitude, because if you moved all the way to the correct altitude, E would become 0. Then you'd have no input, and you wouldn't stay there. You'd start falling again. Okay? So it's not going to correct it all the way. What it'll do is it'll correct it much of the way, and that's good. Now, integral control works like this. What it does is when it sees the error, what it does is it integrates the error. Okay, so it actually integrates it. In other words, if you were 100 feet high for a long time, it would start reducing you, and then it would reduce it farther and farther and farther, and it would keep reducing it until in fact E is driven to 0. Okay, so this is sort of the intuition behind integral control. And this has been used maybe since about 1935, 1940, something like that. Although there's mechanical implementations of this that were used in the late 19th century. So that's the idea. I mean, the math is really perfectly simple. It's as simple as just calculating, plugging these numbers in. Okay, so last time I think Leo looked at how that worked with the plate heating example. And the pictures you see make perfect sense. Here what happens is there is a step in the ambient temperature. If you're open loop, you don't know about the ambient temperature. You don't even know that the plate is too hot. So what happens is the plate heats up, whatever it is, a degree too hot. And you don't know it. You can't do anything about it. It's that simple. Okay, if you have proportional control, what happens is, I think you saw there was a trade-off. The higher the proportional control, the lower the ultimate error. In fact, it's 1 over 1 plus a gain here. Okay? The problem was when you increase the gain, the thing starts becoming oscillatory. And if you increase it too much, it oscillates violently, and even more still, and it actually becomes unstable. Now it's much worse than had you done nothing. Okay? Here's a controller which combines a proportional control plus an integral term. Okay? How did I choose the 1 and 2? They're just neat numbers that gives you a reasonable response. But the response is very interesting. The ambient temperature changes. The plate heats up. This generates an error, which the controller looks at. Now, the controller is doing two things. It's making a correction term, one of which is proportional to the error, and the other is proportional to the integral of the error. And what it will do is it will crank down the heat and hold it down as the temperature is dropping, and once even the temperature has been driven to 0, it still has, because it's an integrator, it remembers that it should be minus 1 watt. 1 watt less than the normal one. And that's why this works. So that's another way to understand integral control, is to say that it actually figures out and remembers what the correct compensation is to drive something to the zero error state. So that's the idea. And you can see exactly what it does. It does it very, very nicely. Drives it to 0 here. Okay. Well, let's look at the general case. The general case, this happens actually quite generally. And you say that a control system or a feedback system, or just a feedback system, has integral action. That's one name for it. If the loop gain, which means either P or C or both, has a pole at S equals 0. And that implies immediately that the closed loop transfer, doesn't imply this. And the closed loop transfer function is stable. The trick is actually to achieve both of these. That's the trick. But if you can achieve both of these, then in fact, the sensitivity at DC is 1 over 1 plus L. L is infinity at s equals 0, so that's 0. That says a lot of things. It says, for example, that if you have a constant reference input, the error is driven to 0. You get 0 steady state error. So that's why it's widely used. In fact, almost universally used in all industrial control systems. Automatic control is integral action. So when you dial up some number on a furnace or something like that, like 731 degrees, given everything else being constant, it will go to 731 degrees. It will track it. That doesn't matter if you open the door. Doesn't matter if the heating coils are getting old or if the supply voltage to the building is 2% low that day. Doesn't matter. It will track to 731 degrees. So that's the idea. Now it also says, by the way, that you get this sensitivity, which is basically 0, at least for long time scales. It says it's totally insensitive to changes in the plant. So that's the key. Now in this case, you often call this reference input the set point. And so that is in fact what the knob would say on an industrial control system. It would say the set point. In fact, you'd see two things usually. You'd see something that says set point, and right next to it would be something that says temperature. And everything else being equal, they should line up right next to each other like that. Usually they're on 2 bar graphs like that, and they line up like that. If you mess with the system, the set point, the temperature will sort of move up or something like that. Then the control system will take effect, and it will move back down, and it will lock right back on. So that's the way that works. So it says if you have integral action, whenever you change the set point, the output will eventually track it. So for example, it will absolutely annihilate constant disturbances. Okay, so for example, if you have a constant output disturbance here, the transfer function from here to here is minus s. That's the transfer function from d out to y. And the steady state error induced by a constant is therefore minus s of 0 d out, which is 0 because s of 0 is 0. So it says that integral action, if there's an output error like this, will eliminate it. And in fact, if you want to kind of understand intuitively what it's doing, because as an integrator, either here or here, it says somewhere there's some memory of constants. And so what it does is it dials up a u which compensates for d out. It figures out what u compensates for d out, and then it remembers it. This is what a proportional controller cannot do. It has no memory. An integrator has memory. So that's basically the intuitive idea. So people call this asymptotic disturbance rejection, because it means that it says that disturbances are completely rejected as time goes on. So as time goes on, it's completely rejected. And this works just as equally well if P or C has a pole at s equals 0. It doesn't make any difference. You get no, this is what happens, right? So that's sort of the idea. Similarly, you have zero static sensitivity, because if you work out the following, suppose C has a pole, but P doesn't, and T is stable, then you have T of 0 is 1, and that's completely regardless of P is 0, because this number here, when C is infinity and P is not, and P is also not 0, then this thing here simply has the value 1. And it's completely independent of the value of P, provided P is actually just not 0. 0 would be the only one where you might have some trouble here, because then you'd have 0 times infinity, and you'd have to figure out, work out what that does. Okay? So in other words, the sensitivity to changes in the plant is actually, it's not small, it's 0. It's just nothing. It's just not there. So it's completely insensitive to even very large changes in the plant. And it's insensitive as long as the closed-loop system remains stable. It's possible, of course, for the plant to vary enough that the whole thing becomes unstable. So that's, other than that one change, that's the way it works. Okay, so the question is, how do you choose the integral gain? Well, the basic trade-off is this. If your integral gain is too small, you get asymptotic tracking, but you get it only after a very long time. That's what happens. In other words, if you go back and look here, everything we've said so far has been qualitative. It just says there is a pole. We didn't say anything about the residue or anything like that. And if you figured out, if you wanted, you could take Ki equals 10 to the minus 8. Okay? You could. That would be sort of the safe thing to do. What would happen then is, sure enough, you would get asymptotic rejection. But it would happen over a time scale which is extremely large. Okay? Now the problem is, if you make Ki too large, you have the same problem you had with proportional control with instability. In other words, if you make Ki too large, you get, first it becomes oscillatory and then unstable. And in fact, it's even worse than proportional control. In other words, that a system will rapidly become unstable as you increase the integral gain. So basically, what this says is it's the same sort of story. It's a trade-off between stability limits you, and if you make Ki too small, what happens is you get integral action, but only after a long time period. So that would be sort of the idea. And let me just show you quickly what the type of things, what might happen in these two cases. So here's an error or a disturbance acts on a system at t equals 0. And suppose, let's say that that's the response if there's no control of any kind. With a nice proportional controller, you might get a response that looks like that. Okay? And this is good. It says basically that you have reduced the error from this number down to that one. That's with proportional control. Now, if you have integral control, qualitatively, this thing's going to look something like this. And it will go to 0. So this is with integral control, like that. Now, it'll go to 0, which is great. The question is the time scale. If I make Ki too big, this thing becomes oscillatory and it starts looking like that. And if I make it much bigger, it'll actually become unstable. Okay? If I take Ki too small, let me show you what you get. And you can actually easily figure this out. I'll show it on a different time scale. So here's that's the open loop response to a step disturbance. Okay? If you make integral action if you make Ki too small, you get this. Here it is. This is so basically over a short time scale, all that happens is you see the proportional. That's as if the proportional thing. This is because Ki is so small that the correction signal, which is Kp times E plus integral E times Ki, takes a long time to build up a reasonable term. So what happens is this continues for a long time at the static error, and then eventually on another time scale starts going down. So sure enough, your error is eventually corrected. That much is true. But the point is it takes a long time to happen. Now maybe that's okay, right? Maybe it doesn't matter if you're flying 250 or 300 feet low for 50 miles. I don't know. I actually don't know. Maybe it is okay. In which case, fine, no problem. Well, in fact, you might keep Ki low in order to be safe, because you certainly don't want something like an altitude hold control system to get even remotely close to oscillatory, let alone unstable, right? So it might be safe to choose something like this. Another example of something like this would be a speed controller on a car. So an auto, one of these things that will hold you at 55 or 60 miles an hour. And in fact, actually, if any of you have cars with this, you can try it, and you can try to figure out if yours has integral action or not. You know how you can tell? If you're low under the set point, and you put your foot on the accelerator, you'll actually feel it move. And if it doesn't move at all for a given error, that's actually proportional control. But in fact, what you'll find is if you stay low for a while, it's going to start pushing harder and harder on the gas. So you'll see that there's an integral control. Okay, so this is the intuitive idea behind the trade-off. All of this we can analytically verify, but this is the intuition behind it. Okay, so let's actually take a look at how this works. Here's an example. It's the heater example. The controller is 1 plus Ki over S. If I take Ki equals 0, I get this response. And the open loop response looks something like this. So with Ki equals 0, I've at least divided my error by a factor of 2. I guess that's pretty good. All All right, if I take ki equals 0, I get this. If I take ki equals 0.2, I get this. These are going to go to 0. This is ki equals 2, is this curve in here, which is a very nice one, in fact. I think you can see. That's probably that's an awfully good design. And for ki equals 8, you can already see that the integral term is already clearly picked too high. So in this example, something like ki equals 2 would be just about right. So that's this is an example about how, you know, what the trade-off is in the choice of ki here. Okay. So there's various other ways that these are described. For example, instead of kp plus ki over s, it can be written out this way, and you can easily work out what these are. For example, k is kp, and then you can work out what t int is in terms of it's something like it's some ratio of kp and ki. Is what it is. Here, t int is called the integral time constant, and 1 over t int is called the reset rate. And these are the numbers. These are the descriptions that you would see in an industrial controller. So if you actually walk up to an industrial controller, you'll see a knob that says gain, and you'll see a knob that says reset rate or integral time constant. You'll see these. And they refer simply to, it's another way to determine kp and ki. So that's all. It's no big deal. I guess this is just k over t int is equal to ki. So you can calculate t int from that. And the basic idea is for a constant error e, it takes about t int seconds for the integral action term to equal the proportional action term. So that's the meaning of that number. Okay. So a couple other comments are that in fact you often get, there's many cases where you get integral action for free. And what that means is basically all that matters is that you have a pole in the loop gain at s equals 0. That actually often happens for many systems, strangely enough. For example, if you have a system like an electromechanical system or something like that, where the input is something like a force and the output is a position, you actually get, well, this is here, of course, is just Newton's law. It's F equals ma, which, of course, you now know how to write F equals ma. It says that the input-output relation for a mass, according to Newtonian mechanics, is 1 over ms squared. Right? So that's your new way, by the way, to think of F equals ma, is when you see a mass from now on, the transfer function from force to displacement is 1 over ms squared. But in particular, it's got two poles at s equals 0. This is kind of obvious, right? I mean, then you think, I never thought of a mass before as being unstable. Have you? But on the other hand, if you think about what a mass is in outer space, of course it's unstable if the input is a force. If I put a little force on a mass and let go, what happens to a mass in outer space? It acquires a velocity, and then after you let go, it keeps going. Its position, its displacement grows with time. Okay? So you can call it unstable if you like, I guess. But anyway, that explains it. But what this says is that, for example, if you have a satellite or something like that, or an aircraft, or any kind of electromechanical system, it says usually if you're doing position control of any kind, your controller doesn't even have to have you will get integral action for free. Okay, so that's true for in fact almost all electromechanical systems. You get something like that. In fact, it's even true if you consider the output to be the velocity, because then you get 1 over ms, and you still have a pole at s equals 0. Here's another practical example: is if you put a voltage on a DC motor, and the output's the shaft angular velocity, the plant looks like k over js. There's your pole at s equals 0, right? And the poles there's a real negative pole, and there's a pole at s equals 0. And so if you simply put a control system around with an electromechanical system or DC motor, you'll get integral action for free. Period. It just works that way. Okay. So let me summarize what all of this stuff. The first thing is that this is widely used in industry. Widely used in industry. In fact, I guess depending on, I don't know who you talk to, I guess PI controllers accounts for something like, there's another term actually, you wouldn't be surprised what it is. It's PID is what's actually used in practice. D is, of course, a derivative term. So it's no big deal. So these controllers for industrial control are used in something like about 95% of all cases. So if you simply walk into a factory or anybody doing some processing or anything like that, if you look at industrial control, something like 90% of it is PID. That includes, by the way, a lot of the even pretty sophisticated control systems like mechanics on for CD players, transport stuff. Much of it is very simple PID control of it. More and more of it is becoming much more sophisticated control, but a lot of it is PID. So you'd be surprised, you'd be amazed to see what you can do with stuff this simple. Okay, so the point about it is, if you have a pole in the loop gain, what you get is 0 steady-state tracking error, 0 steady-state effective constant output disturbance, and absolutely 0 sensitivity to DC plant gain. This is to be compared with proportional control. Now the disadvantages, there's a couple. One is that the open loop system is unstable, okay? And so what this says is you have to be very careful to make sure that, for example, you don't lose your sensor signal. If you lose your sensor signal, you are in deep, deep trouble, okay? So if for example, or if your sensor becomes faulty, you are in deep, deep trouble. For example, if you take an aircraft altitude hold system, if it's a proportional controller and your radar thing goes nuts and is simply off by a couple of 100 feet constantly, your proportional one, it'll change the altitude until the two effects balance. Okay? Hopefully that'll be with a positive altitude. Otherwise you're in trouble. I mean, if it's off by enough, then even with a proportional controller you're in trouble. Now with an integral controller, you're in deep, deep, deep trouble because there'll be an error. The controller will say, oh, airplane's not low enough. No problem, we'll just back off on the thrust some more. It'll wait a little while and says, not low enough still? I'm backing off even more. And so I think you see that's the whole point of integral control, right? Is that it basically looks at it accumulates. What it does is its action strengthens with time. If you're low for a long time, proportional control doesn't care how long you're low or hot or cold or whatever. It simply calculates a reaction and makes a reaction. It depends on how hot or how cold or left or right or whatever it is you're controlling. But it doesn't depend on the time. Integral control says, fine, I'll just turn the knob and I'm just going to keep turning it until I get the effect I want. And if the sensor's wrong, you're in deep, deep, deep trouble. So whenever you have integral control, there's lots and lots of mechanisms that test to make sure the sensors are right, that if you hit limits, alarms go on and all that kind of stuff. So that's a great disadvantage. In fact, in a lot of cases, that's why people simply just don't use it. Okay. And the other problem, of course, is that if you have excessive integral gain, it yields closed-loop instability. And the basic design trade-off is how fast you can affect asymptotic tracking versus stability. So as you increase the amount of integral action, the first thing you see is good. What happens is that you get the effects of integral action over a shorter time period. You keep increasing it, and now your closed-loop poles are going to become complex, first thing. Soon enough, the damping will get small, and you'll start seeing oscillations. And if you keep increasing the integral action, it'll lead to instability. Okay, so this is sort of the overview of that. But this actually explains a reasonable fraction of automatic control systems that are used. So this is like most motor control, even very fine, sophisticated control. A lot of it is done just with PI and PID control. Okay, so that finishes up this topic. And what we're going to do now is, I don't think you have these lecture notes. Neither did I 35 minutes ago. But I do now. So, these are very, very fresh. So what we're going to do is look at a couple of applications. This may grow to 3, by the way, by the time you actually see it on Wednesday. But right now, it's 2 applications. And it's fun because these are, actually we're going to do it for 2 reasons. One is it'll illustrate all the stuff we've done in the class. And the second is that they're fun. These are good things to know about. So if you do electrical engineering, computer science, anything mechanical engineering, these are things you need to know about. So so it's an excuse for me to tell you about something, some important device, and it's also an excuse for us to go over stuff we've done. So, but as with integral control, in fact, all of feedback control, basically there's nothing new here at all. Nothing. We're just applying stuff from the first half of the class. So the first topic is oscillators, and I guess you probably know what an oscillator is. It's a device that generates a sinusoidal signal, although it could be a non-sinusoidal signal. But it generates, it's meant to generate a periodic signal, like a sinusoid. And so this is actually often done. Some people would even claim universally it's done with feedback. This is basically how oscillators work. You can anytime I see an oscillator, I can always reinterpret it as a feedback system. So, and in fact, in some cases, this interpretation is very explicit. In other words, it's drawn and analyzed and thought of as a feedback system. But even when it's not, it is a feedback system. So here's the basic idea. You want the system now, but up till now, it was an automatic control system or an amplifier or something like that, or some piece of signal processing equipment. And of course, then we presume we wanted the closed loop system to be stable, right? We wanted it to have, say, I don't know, certainly poles with negative real parts and so on. Of course, you can also use a feedback system. It might be to control an economy, in which case, of course, everything switches, and you want all your poles as far to the right as possible. You might or might not like imaginary parts to your poles, right? Because those would be periodic depressions and things like depressions and boom cycles. So probably there you'd want it real and as far to the right as you can get, and that would give you the growth rate of your economy. Okay, so most of the stuff we do in this class to the left is good and to the right is bad. All right. Now in this case, if you want to build an oscillator, here's what you want. You want the poles, you want at least a pair of poles to be right on the j omega axis. That's what you want. You want the closed loop system to have a pair of poles right here, and that's going to be an oscillatory term. That's what you want. Now, what about the other poles? Well, if you had a pole out here, this would not be good, because that would represent a growing exponential term, and your oscillator signal would then consist of an oscillatory term plus a growing term, and this would actually swamp this out eventually. So what you really want is this. If there are any other poles at all, which sometimes there aren't, you want them to be over here. And the truth is, you don't really care very much where they are, right? So this is okay. If these were the poles of a feedback system, this would be fine with you, because these two terms would represent an oscillatory terms. These three here would represent, this would be oscillatory decaying terms. This would be a real exponential decaying term, right? And so these would fade out. And in fact, the time it would take for these to fade out would be determined by this distance, right? Because that would be the real part. That's sort of well, of course, these are the dominant poles, but in an oscillator, you might call this something like the dominant non-oscillatory pole or something idiotic like that. Basically, it's this distance that would tell you how soon these other non-oscillatory terms would die out. That's what that would tell you. Okay, so the specs are that we need poles now right on the j omega axis, and we need the other poles to be in the left half plane so they'll decay and go away. That's what you want. Okay. So we actually want a closed loop pole. That's the same as the loop gain being -1, because the sensitivity is, well, it's that's the closed loop transfer function is L over 1 plus L. And so you want, but the main part is the loop gain here. You want this to vanish at s equals j omega. So you want the loop gain at a frequency omega to be -1. So that's the idea. Actually, I should call this omega 0 here, something like that. In other words, you want the angle of the loop gain to be 180 degrees, and you want the magnitude to be 1. And the intuition is really, really simple. It says basically, if you have a feedback system like this, there's a minus sign there. It says that the net phase change around this loop should be 180 degrees. Okay? If that's 180, then you throw in the 180 contributed by this minus sign here, this negative sign, and you get 360. And that says, makes perfect sense, it says that you'll get an oscillatory response if at a certain frequency, the sort of the loop gain all the way around, including this minus sign, is 360 degrees. In other words, when a sinusoidal signal transmits through here, it comes back right to the input again, exactly what it was when it went in. So the idea is it regenerates itself. So that's the basic idea. And so in fact, that was the original analysis. This is originally how oscillators were thought of. Unfortunately, this works a little bit, but doesn't allow you to design actual oscillators, which actually confuse people. Because in fact, what this kind of analysis, informal loop gain analysis, doesn't tell you is about these other poles. And if they're over here, you're okay. If you have one over there, it doesn't work. Okay, so we'll look at an example. It's a classical oscillator. It's a famous one. Here it is. It consists of an amplifier and 3 RC sections. Okay? I made them all R and all C. It doesn't matter. These can have different values, different C's, different R's. And then, of course, the algebra of working out the transfer function from here to here becomes a complete nightmare. But people have done it. You could do it. It's not hard. I just made them all equal for no particularly good reason. So first, actually, let me start with just the intuition behind this. Actually, that's a very good way to start. Before you do any math, is just figure out the intuition behind it. What does the, first of all, let's think of the feedback network, which sort of starts here and comes out here. What's the transfer function if we call that F from here to here? And don't even look down at, oh, it's already down there. That's too bad. Okay, what is it at DC? Don't look at the formula. What's the transfer function from here to here at DC? It's 1. It's got to be 1. If you put a volt here, then in static steady state, this thing will be a volt. What does the time response look like? If the voltage here is 0, 0, 0, and this thing flips from 0 to 1 volt, what happens? Just intuitively. What does the voltage here do? It rises, right? If there was nothing over here, that thing would rise exponentially a la 101, right? With a time constant of RC, right? Okay. Okay, but you have this. That's actually from 102, I think. That's from one of the examples early on in 102. And this is another one. So let's just figure out roughly what does it do. This kind of goes like that, this voltage. This one actually takes a little bit more time getting started, so it actually looks like that. This one here takes a considerable amount of time getting started and then goes like that. So it kind of looks like that. Okay? And in fact, what it basically says is that there's a bit of a delay, but eventually the step response to here rises to 1. Everybody got that? So this sort of makes perfect sense, right? It makes very good sense that at high frequencies or small time, the response here is exceedingly small, right? Because basically, the only way you ever get any voltage there is to have this thing charge up to an appreciable voltage so you can charge it. Okay? But this doesn't charge up to an appreciable voltage until this does. So in other words, although it's really described by a differential equation, you can explain it intuitively like this. Here would be the intuitive explanation. This voltage pops up to 1, which starts charging this guy. As soon as this guy gets some appreciable voltage on it, he starts charging through this resistor this one, which, by the way, bleeds off some of the current from this one, so it's charging less fast, if you want to be accurate about it. This guy starts charging up, and eventually, when this charges up to appreciable voltage, current flows through there and lands here, right? So now you can sort of see that it's going to be a delay. Okay, so there's a delay, all right? What happens when you put feedback around a delay? What happens when you put feedback around a delay? Yeah, it can get unstable, right? Which you know from being from adjusting the water temperature in a shower. I'm sure you know. Is your classic example, right? Right. Yeah, good case where excessive integral action would be unwise. Yeah, so it can go unstable. Of course, in this case, that's what we want to. That's exactly what we want to do, right? We want it to go unstable. So delay, which in a normal feedback situation is your enemy. If you're building a feedback amplifier or something, or an automatic control, it's your enemy. Here it's your friend because you want to make an oscillator. You want delay. That's essentially what gives you oscillatory response is feedback plus delay. Okay, So that's the intuition. Here's the transfer function. And what we need to do is, I guess the loop transfer function is A over this. That's L. And what I want to do is pick R, C, and A. These are my design variables. So that this thing is equal to -1 at S equals J omega 0. That's my job. And if I wanted to, I could just dive in and make this an algebra problem, because it is just an algebra problem, and I could solve it that way. But actually, that's, I think, a very bad way to do it, although you get, of course, the right answer. The right way to do it is actually think about it seriously, and look at it. Also, the algebraic method doesn't work when there's 9 R's here, right? Or something like that, or some horrible thing here. So a good way to do it is to look at this thing and to say, how would you choose RC and A to make this thing equal to -1? And there's a couple of things you would do. The first thing you notice is, well, it only depends on the product RC. That's the first thing. That's kind of obvious here, right? That the transfer function from here to here only depends on the product RC. I can scale them all by something. That's fine. What about A? Well, the interesting thing is, if the loop gain here were equal to like -7, if this were equal to -7, I could choose A to make this thing -1, because I'd choose A to be 1/7. If this thing were -0.03, I could also choose A to make this thing -1, because I can choose I could then choose A to be 33.33 or whatever, right? So what you see immediately is, if you can make the phase of this thing without the A, if you can make the phase of that thing equal to 180 degrees, then you can adjust A to make this equal to -1. That's the idea. And so how would you get the phase of this thing? Well, of course, you would do a Bode plot. So here's a Bode plot. And this Bode plot, by the way, absolutely confirms everything. There's the DC gain, 0 decibels. You can check here. It rolls off very rapidly, I guess 18 decibels per octave at high frequencies. That's related to this thing being very, very slow to start. So there it is. And here's the phase shift. Now our job is to find out when this thing hits 180 degrees. But of course, we'll take 180, we'll take -180, we'll take minus whatever 180 and 360 is. We'll take that. We'll take any of these numbers. And if you look here, we can accept this number, -180. That's the same as 180 for us. And you draw it across there. We can also take, not 360, but one down here. Well, the fact is, it's never going to get down here. This is the only possible, that's it. That's your only choice. So there's only one, and then you look down here and you say, wow, that's great. That's 1, 2, that's 2.5 times RC. Sorry, 2.5 over RC is the frequency. So what's interesting is, just by looking at a Bode plot, we were able to find out the frequency that this would oscillate at, which is precisely 2.5 over RC. That's the frequency. Now you look up here to find out what the gain is, and the gain turns out to be about -30 dB, so on, and that's it. So now we have a rough idea of what A has to be. A has